So thank you very much for joining the talk. So my name is Vladimir Vishnevskii. I would like to offer this topic that is called Variadic templates and parameter packs. So why I would like to offer this topic, I find it to be important. Yeah, so this is really essential for modern C++ design. This is a feature of the language that enables a lot of different standard and third-party facilities, and at the same time can also be used not only for just complex designs and complex frameworks, it also can be useful for just creating flexible custom facilities. So, and efficient. This is a C++ fundamentals talk. Yeah? So we will be exploring some concepts. We will not go deep there. So we will also look at some applications. And I think the best outcome will be if we actually familiarize with those concepts and see how they can be used, and also have some direction for further learning after this talk. And I'm also trying not to target some specific standards. So most of the talk is, of course, dedicated to C++ 11 and beyond, but I try to use the most kind of generic implementations, but I will be highlighting when some specific standard features are used. Okay, so before we start with Variadic templates, I would like to also maybe make a small refresher about templates in general. Yeah, so very, very, very short and without that much of the detail. So I think everyone, so I'm expecting that we are all familiar with this syntax. Yeah, so here we have class or structure template and a function template. Yeah, so let's look a bit with more details into the class template. So here I extended a bit example. So we have here static vector class template. So this is some vector-like container that can have pre-allocated storage of some compile time specified class size. Sorry. So this template has two parameters. The one is time template parameter that is here has name t, and another one is a non-time template parameter that is capacity, so the maximum number of elements that it will be able to store. So the way how this will be handled and how we can use this is depicted on the next slide. Yes, so to use the template, we need to instantiate it. Yeah, so and how the instantiation and then substitution of the parameters by arguments will be handled by the compiler is depicted here. So when we instantiate template and provide the arguments for the template parameters, those parameters inside the template body will be substituted by provided arguments. So it will produce the concrete class. It will not be template anymore. And for each of the parameters, the corresponding argument will be just used instead of the parameter name within the code body. This is for like non-variadic templates. Yes, so here we have an integer that will be used instead of t, and we will have just a value that is a non-time template parameter, that is an argument for non-time template parameter that is 10. It will be then used whatever capacity parameter was used inside the body of the template. So this was, of course, available before C++ 11, and it was possible, of course, to have more template parameters, multiple template parameters for class template or for function template. And of course, it's much more about templates that, so there can be also template parameters. There's much more information that is available for templates, and it's much more complex topic, but I think it will be sufficient as an intro for our topic. What I wanted to highlight is that it was possible to have multiple template parameters, of course, but it was not possible before C++ 11 to have actually arbitrary number of template parameters. Yeah? So there were techniques to somehow work around those limitations, but generally on the language level, it was not supported. It wasn't possible to have arbitrary number of template parameters and be able to handle this somehow in a generic way. And this was introduced in C++ 11 in the form of the variadic templates and parameter packs. So the following syntax became available in the language. Yeah? So here we have now the variadic templates and corresponding parameter packs. Yeah, so here we have function, here we have a template parameter packs. So those specify the types. And we also have, for function templates, we also have a function parameter pack that actually corresponds to the parameters of the function. Yeah, so those, it will then hold the values already, not the types of the arguments that we provided when the function will be instantiated and called. Yeah, so a couple of details about the parameter pack. Yeah, so parameter pack is a named entity that represents a group of arguments. Those can be types of values, depending if it is a template parameter pack or a function parameter pack. And those packs, they correspond to those types and values that were used to instantiate the template. Yeah, so a pack can be empty. It can be zero or more. It can have zero or more items. And inside the template body, packs should be explicitly expanded. So we should specify how those packs are used. So it's not that we just place them and they will be substituted in the trivial way as it was in the non-variadic template, but we need to explicitly specify how they will be expanded and propagated inside the code of the template. And this can happen within some language, standard specified contexts. Of course, there are, so in the talk, I will try to cover most of them, but the comprehensive description is, of course, available on the CPP reference and, of course, in the standard. And there is, but I hope that we will at least cover the most used of those contexts. And let's now look into those application of the parameter packs, how we can use them, and also generally do this using examples. Yeah, hopefully we will cover most of those potential usages. So the first example of this is for the first example demonstrates 3 expansion contexts that I think that are among the most used. So here in this example, we are actually implementing some container or some facility that actually wraps a standard tuple and uses it as a backend storage. So this would be a variadic template. So, and tease is the template parameter pack. And to use some tuple as a storage, we need to provide the arguments for a tuple template. So to say that we are going to store those items in the storage. And this is one of the expansion contexts that is supported for template parameter packs. It actually can be expanded into template argument list. So here our storage T will be a tuple that stores the types with which we will instantiate our tuple wrapper. Next expansion context is actually a function parameter list. So we have those. So here is the tuple wrapper constructor. So we will need to propagate the values with which we will construct our wrapper into our storage. We use our pack and expand it into the constructor parameter list here. And this would basically generate for us the set of parameters of the function based on the types with which the wrapper will be instantiated. And the function parameter pack that is args here, we then expand to initialize our backend storage. So actually in the member initializer list, so we initialize the storage and we just expand the values that will be provided when the constructor will be called into the initializer of the storage. Let's have a bit closer look into how this happens. Just for this example, I think it will be beneficial to also have this kind of substitution layout. So here we instantiate our tuple wrapper with 2 types, integer and float, and we provide some values. And here we see that those types that were used for instantiation, they are propagated into the body of template as a part of substitution. So as we specified during the by the expansion. So, and expansion, sorry, just also probably was already visible from the slide, but to do the expansion, we use the ellipses. Yeah, so on the typically on the right side of the parameter pack, but there are exceptions for this. We will cover them. So here we see that on the right how the code was transformed as a result of the substitution. This is a trivial, these are the trivial examples of expansion. There are more complex, and let's start covering them. So it's not necessary that we expand those parameters as is. So we can actually apply some operations on them. And here, there is also one of the most probably common examples of applying some operation to the parameter, just basically some using forwarding reference with forward. Yeah, so here we have some factory function that would create tuple for us, and it has the so it used the forwarding references to basically perfect forwarding the arguments into the tuple repo constructor, and here we have std forward as an expansion pattern. So this is an expression that will be applied to each item within the expanded parameter pack. And also what is important here, within this expansion, we have actually two packs that are expanded simultaneously. We have our T's that is a template parameter pack with the types, and we also have args. This is the function parameter pack. So basically in this expression, the corresponding arguments will be then forwarded according to the corresponding types with the template parameter pack. Another expansion context, or for actually not looking exactly like expansion, but it is an expansion context, is size-off operator, like this specific size-off that accepts the parameter packs. So it can be used to get the size of parameter pack. It's listed as an expansion context, and it has usage. That's why let's definitely cover it now. So let's look at this potential implementation for makeArray function. Yeah, so like here, makeArray is a helper function that produces array of some specific types from the provided arguments. So here internally, what is happening is that we need to somehow, especially before C++ 17, yeah, so we need to figure out the size of the array on the compile time. And here we know that we will that this function will have the parameter pack of that size, and this size will define the size of the resulting array. So we're just using size of here with the passing the parameter pack. Over it is listed as expansion. You see that the syntax is slightly different here. We really do not expand the pack. We don't use ellipses somewhere inside the size of us. And here we also have another expansion pattern. We use forward, but also construct the object of a type T. So this is this pattern became a bit more complex. So we have a construction of objects for each item within the argument parameter pack. Sorry, function parameter pack. Okay. A bit of the bit more extended examples for those expansions that we already saw. We can expand packs into initialize a list. This is a quite used technique because we, if we expand something into some form of into initializer list or in some container, we actually can handle this within the function body in a quite convenient way within the loop. For example, here there is some implementation of a sum function that receives the values and just returns the result of the sum of all of those values. It is implemented in a way that we just have the initializer list within which we expand the function parameter pack and then just use the standard loop over these elements and just add them together. So we need, for initializer list, we need the common type That's a limitation, of course, because we initialize a list should contain items of so values of the same type. So here we can use some initial value that is the first argument when the sum function is called to as a result type and also as the type within the initializer list. And this can be const expression since C++14. So C++14 significantly relaxed the requirements for const expression, so it should not be recursive anymore. We can really write this construct and have this evaluated on the compile time as a const expression. Okay. Another application for initial expansion in initializer list, especially before C++17, was actually to perform some operations on each item of the function parameter pack. Here, this example is a bit more complex. Let me inspect it and clarify what is happening here. So we expand function parameter pack here in the initializer that actually int initializer list. Yeah, so it's instantiated with int, so it expects ints in the initialization. But what is happening here? We have some operation that we need to perform on each item within the parameter pack, on each argument that was provided. This operation is then followed by comma operator, and the comma operator is quite interesting one because it actually evaluates the left operand, discards it, then evaluates right operand and returns the value of the right operand. And also the type of this operation will be the type of the right operand. So what is happening here is that these output into standard out is just discarded or it performed, it is evaluated, it's discarded, and then the zero, the value that stands on the right of the comma operator, is actually propagated into the initialization of initializer list. So this is a bit of the technique that is used to really perform an operation on each item because we cannot just simply loop through those items. And what is important here, we do not need some common type for that. All of those those types of those arguments that are provided here, so the arguments here, they can all be of the different types. We cannot put them into one container because we don't know in general those types. And here they are handled generically. So shift operator in stdc out, it actually can handle various types. And if it can handle it, so this code will work because it's, again, just the arguments, they are just propagated into the operation that can handle them. So without knowledge of the types that are used there. That were, okay. So here also not necessarily initializer list, also array can be used there. So just different facilities, but the technique will be the same. Okay, another. Let's do that after, yeah, okay? Let's do the questions after. So another technique that and actually another expansion context that I also wanted to mention. This is available since C++20. This is the expansion in the lambda capture list. So we can expand the parameter pack inside a lambda capture list. So that's how we can propagate those values into lambda. And then we can use it inside lambda function. Of course, we can also use the reference. We can capture those values by references. Here, please consider that, of course, capturing by reference, the same constants should be applied as with always passing something by reference. So here we here not the values are passed by reference. So our do something async function also now receives references, so somehow we propagate it by references. So the lifetime is considered to be managed by the client code here. And also we can move into the lambda function now. So here it's an interesting, again, slightly different syntax for expansion. So we expand args into move operation. And here, the ellipsis, it precedes. So it's like looks more like a definition of another parameter pack. But the idea here is that the args, it's a name of the capture within the lambda, and it will store the items that were moved from the context where lambda was created. And what this args is just a name for the capture. It can be different, so it's not that the same name should be used. Yeah, so just I see this pattern quite a lot. Just wanted to clarify that we can rename args here. So it's just it will be then the local for the inside the lambda, the name. Okay. Another expansion context that also is quite peculiar is alignment specifier. So if probably not, there is no daily usage for that probably, but if we develop something like a variant that's supposed to hold, that should be able to hold different types, we need to probably enforce some alignment that can, alignment that will be defined by the types that the variant can store. So here, if there's some just a line from the potential implementation for this variant, and we can use alignment specifier also with pack expansion. The interesting thing here is that as a result of substitution, actually, it's not that the pack is expanded within the alignment, it's that there will be multiple alignment specifiers applied to some object, because that's how actually language uses this alignment, requires this alignment specifier to be used. And so that means that the expansion is not always resulting into like comma-separated expressions, but it's actually really like context-specific. Yeah, so how this is done and how this will be handled within the specific context. Okay, yeah. So here it's depicted for int and float. We have two alignment specifier applied, and also here we also have an extension of our template parameter pack into the initial, of our template parameter pack into the initializer list with size of operator. So this is a normal size of the type. So it's not the parameter pack size of. We just need to figure out what is the maximum, what the size of the array should be to hold the maximum size that our variant should be able to store. Then it's passed into set. Okay. Another example that I think has quite some usage, and also very elegant example, another context that have a lot of usage, and I think very elegant example for it from CPP reference. Actually, it's surprisingly it's not so the example is for actually a standard stud visit. I'm not sure. So hopefully you saw that before. The idea is that we have the variant and we have the stud visit function that applies some actually visitor to the variant, and we can specify the the visitor. It should be some callable object that should have overloads for every item that we would like to visit, and so it will be convenient to use it with lambda, but we cannot overload lambdas basically. So and this overload facility, it just combines those lambdas. Yeah. So this is, and the usage, the implementation of this overload is really is very elegant and quite trivial. So what is happening here? So when we are calling overload, it's initialized with some types. Every lambda, it produces the unique type. Yeah? So this is how it is guaranteed by the standard. So we have a deduction guide. This is a C++17 deduction guide that specify that items that are used for initialization of these overload facilities, overload object, are supposed also will be used as the template. So the types of the items that are used for initialization will be also used as the arguments of the overload template itself. And in the implementation of overload, what is happening? Those types with which it was constructed are actually used as a basis, for this overload. So here we have expansion into basis. So our types that are template parameters for our overload, they are now the basis of the overload object itself, and also the call operator is also exposed to be available from the object, from the basis. So it's exported from the basis into the overload object itself. So this is how this works. So that means that when this will be called within the visit function, the corresponding overload, so corresponding call operator will be called. So it just aggregates several lambdas into one object. That is actually quite convenient. And also here in this example, it's not present, but also it is possible to call to initialize bases, also expanding the names of the bases in the member initializer list. Yeah. Okay. So far we saw that to handle the parameter packs, two primary approaches were available. Yeah. So we had we could use recursion. This is primary was C++11 technique. We also could expand our parameter pack into some initializer or into some container, depending if we try to implement const expression function or not, because const expression was quite limited for C++11. So there were some techniques available, but there were no. So they all required a bit of complexity, let's call it like this. And C++17 just introduced special facilities to actually handle the packs and to apply some operations to each element of the pack, the so-called fold expressions. And using C++17 fold expressions, our sum function that we introduced earlier can be actually implemented in a quite simple way. Yeah, so this is the fold expression here, this ellipsis within operator. So the fold expressions, it's an expansion of the pack in a quite specific way. We will cover this. Here we have a binary left fold, so this so left to right defined where the ellipsis actually stands, and binary because we also have some form of initial value. So this would be expanded and substituted in the following construct. Yes, so we have, if we call this function with some parameters, with some arguments, it will be substituted in the following construct. Yeah, so we will have initial value to which the first argument will be added, and to the result of this argument, the second argument will be added. So I mean, the initial value is actually the first argument of the function call. Yeah, so let's to be more precise. Yeah, so when we call it here, this would be 1 to 1. The 2 will be added, and everywhere here we have different types as long as operations are defined for those types and compiler can support this, this will be a valid construct. So we do not need to deal with any types here. So we just apply the plus operator to any item within the pack. And this is the binary fold. There are several types of folds. So we have unary folds, we have binary folds. Unary fold doesn't have any values, just operates only on the pack items. The way how this is expanded is depicted here. So yeah, so what is unary and right? Sorry, right and left. In the right case, we have first argument to which. Yeah, so here we can see that. Yes, so in case of right fold, so we have the first argument, and then there is an operation with the result of that is evaluated, kind of applying the same operation recursively to the rest of the pack. And opposite, we first apply operation between first two elements of the pack, and then handle the rest in case of left fold. Yeah, so this is how. I'm sorry, don't. Yeah, I thought that. Sorry, I thought that there is a pointer there. It's not there. Apologies. Yeah. Okay. Better not to move. We can look at this a bit later, yeah, so that afterwards. we can also use unirefold here. So this is some implementation with unirefold. It has, from my point of view, it's not ideal implementation because the interface for this function is actually not clear if it handles the empty pack. And as we know, the packs, they actually can be empty. So the call can be without any arguments at all. So from design point of view, yeah, it basically hides the fact if it looks a bit better if there is an explicit argument for one single value if we require that it should be there. Because actually, the plus operator and the fold expressions with plus operator, they do not support the empty packs. Yeah, so this will be a compilation error, and from the design point of view, it's not clear if it should be actually used like that. Just wanted to demonstrate this, that we can use actually unirefold here as well. So that's how it looks like. Yeah. So then, just without any initial value, there will be a summation for all the items within the pack. For the empty packs, only 3 operations are actually supported, and they have default kind of results if applied for empty packs. So this is the logical AND, logical OR, and comma operator. And logical AND applied to empty pack evaluates to true, logical OR false, and comma evaluates basically to void expression if no parameters, if the pack is empty. So yeah, if we look at how this would look like in the code, yeah, so if we call our facility, so all are true or at least one is true, yeah, so that are just using those or logical AND or logical OR operators for the packs and call them with empty packs, those static expressions will evaluate to true. Yeah, so I mean those static expressions will pass. Static assert, sorry, will pass. Okay. So far we were using those. So we were just reviewing only simple expansion contexts where basically where we were propagating the packs or handling them into other either containers or in the trivial like arithmetic operations, but it's not necessary should be that trivial code. Yeah, so here is a really simple facility that performs operation that basically implements the deletion of some set of paths on the file system. Yeah, so some resources on the file system called delete all, and it just deletes all the paths that provided as arguments when it's called. Alternative implementation, it would require that we either pass the initializer list there, or if we pass some form of the some temporary container. Here we can just list them. So this is just a convenience and convenience facility. And to implement it, we can have different approaches. Yeah. So the one is basically to expand this into, again, internally into initializer list, convert everything to paths, so basically initialize paths from everything that is provided. If it will be possible to convert, then we will not have any compilation issues here. But we also can do this using fold expression. And with fold expression, we can just apply some function to every item of the function parameter pack. But we just perform any operation. So we just perform we just call a function with each item within the parameter pack. We can have more complex logic that will be performed on each item of the parameter pack. We can just encapsulate it into lambda or just into function and call it the same way as we did before. So again, lambda can be generic, so that means that we also do not need to figure out what type our arguments have. What types do they have? Okay. A bit more examples of the complex logic in the fold expressions, a bit involving example here, but actually quite interesting, I think. So this is a function that searches for the item in the function parameter, so in the function, that searches for the function argument that satisfies some predicate. So find first if. So to find something inside, so we again will use the fold expression. Within the fold expression, we will search for this item, and then we will assign this item to our result that we will need to have outside of the fold expression here. So here we use the common type standard facility. It will try to, if it is possible, it will find the common type that can, to which the items within the parameter pack can be converted. So we have we will have one default initialized. It also should be default initializable in this implementation, and then inside there will be this complex inside the fold expression. There will be a complex expression where ternary operator will be used. So we apply the predicate, and then if the result of the application of predicate evaluates to true, for the ternary operator, we will assign the result to this argument for which it evaluated to true, and we will again use the comma operator to actually specify the result of overall operation to be Boolean and true. In case if predicate doesn't evaluate to true, it will be just false here. And this will be all done in the fold expression with logical OR operator. So as soon as the predicate will be satisfied, the result will be assigned, the true will be returned. There will be no further evaluation of the predicate, so it will be shortcutted, so the item will be found. What is interesting, starting from C++20, we also have even optional that can be used as constant expression, so we can even have more reasonable interface here and also avoid a requirement that should be default initializable. Yeah, so we can use optional and return it in exactly the same way as we did before. Quite important that we have quite many facilities that are now available in the const expressions, and they should be neglected. Okay. Okay. Another topic would be, we saw the parameter packs. We could actually operate on them. We could transform them. In some applications, it actually would be quite convenient to store them. And how it can be done? Using a very simple facility that is called type list here. So what it is, it's actually just a Variadic template that has no fields, nothing. And how we store the pack, we just actually instantiate this one with the pack. And if we just create an alias where the pack is used, here just explicitly we use some set of the items, some set of the types. This would be our type list, and those list of types there internally then will be our pack that we will store. So let's look at the example. Yeah. So example, let's assume that we have some scheduler that corresponds, that can be used to schedule some events. Yeah. So we implement some class scheduler, and it's a Variadic template, and it's parameterized by the event types that it can schedule. Yeah. So we can then internally store the events that it can support as a type list of the events, and we'll call it supported events. So we can have then a function, like a standalone function, that will be using the scheduler to schedule some event. And we can make it also a Variadic function that will always be parameterized with the types of the events that scheduler can handle. Or we can just make the scheduler just a template parameter, scheduler T here. So because that's how we can actually substitute scheduler by some other implementation by mock. And inside, what we can do, we can just check if, for example, the type that we want to schedule is supported by the scheduler. So for this, we need to figure out if the type that we want to schedule is in the list of the supported events. For this, we need to have a facility is in list, and we need to implement it. And in this implementation, so this is in list is basically what it does. It just extracts the pack from the type list. So we can look here. So it is a variadic. So it's a variadic function template, and it expects as an argument type list that is instantiated with a template parameter pack. So that means when it is called with some type list, this instantiation will have access to those types within the type list. And it is forwarded into the function that is in pack. It's a more generic function that just can check if the type is in the pack. The type T is in the pack TS. So so when instantiated, these type list matches those types from the type list here. And how we can implement isn pack. I also want to use this opportunity to show how handling of the specs actually evolved as a part of different metaprogramming techniques. So this isn pack in C++11, if we wanted this to be available in the compile time, had to be implemented only in form of recursion. Yeah, so here we had to recursively try to match one first item of the pack, and then basically propagate the rest of the pack into the recursively into the same function. And this is how this can be done if we wanted this function to be const expression. Due to limitation of const expression C++11. Yeah, so here what is happening, yes, so we have function template overload that actually takes type and the type of the first item, and then just match. If they match, then it will evaluate to true. Otherwise, it will just recursively call this isn't type pack for the rest of the pack. And in C++14, that was already possible to implement it in a much simpler way. So this stud is same. It was used in the previous implementation as well. This is a type trait, so it just evaluates to true. So it has this value equal to true if those types are equal, yes. And this is also can be seen as a meta function, so the function that operates with the types instead of values. Yes. So what was possible since C++14, we could just apply this function for all items within the pack, and just convert that into the list of values, and just use the normal loop to find something there. So this is already not a recursive implementation, although still available in the compile time. So it's a const expression. Here, just a normal loop performs the search for the item that if it evaluated to true. Yeah, so in C++17, this can be done almost as a one-liner. So we just apply, using fold expression, we apply is same trait to every item within the parameter pack using the OR operation. This became much simpler now. Yeah, so this is, and it can be even shorter if we just use the variable template. So basically can assign some constant to the result of the evaluation of the expression here. Okay. How's with the time? I have 15 minutes more. Okay. One standard type that I also wanted to mention in the context of those various pack-related techniques is actually a stud tuple. This is quite a convenient facility because it's enabled by this. So it's the design of this tuple is, of course, based on the Variadic templates, but it also can be used to handle various packs. Because at first it can store the items of the packs. Yeah, so like we can use the tuple to be a storage for the items of the types of the pack. Yeah? So for example, here we say, okay, so as we saw, it's previously now a tuple wrapper example as well. We can also get access to all the items within this using apply function. Yeah? So the apply function can be called on the tuple, and then it can be a generic function where we will have a function parameter pack that will correspond to each item of the tuple. So that means that we can handle those items and turn the items in the tuple into the parameter pack and handle them generically. So this is a C++20 feature that is an explicit template parameter list. So this can be done if we need the types of the items of the tuple, or we can use decal type. Yeah, so just whatever. I prefer this one. And also there are some facilities for tuple that allow to inspect the types of the items. So if we have some tuple association, we can actually figure out what is the type of the, on the compile time, what is the type of the item within the tuple, and also get the size of the tuple. Yeah, so there are some features. Okay, now a bit about more recent additions to the standard, like C++20, although it's really since a while. But in C++20, the so-called abbreviated form was introduced. Yeah, so it of course works for parameter packs as well. Yeah, so here there is a difference. Yeah, so in abbreviated form, we don't need to write template type name. We just use the auto. And this would make this function a function template. Here, the ars is parameter pack. Also, Variadic templates can be, of course, also used together with C++20 concepts. So in both forms, abbreviated and non-abbreviated. So here, we have some concept that constrains the types that should be in the parameter pack. Hope that we are all familiar with the concept. Concept is basically some compile time requirement for the types that can be applied for the template argument to verify if it's actually can be used with the template. So quite an interesting application for this. Let's look at some not supported code. Yeah, so we cannot actually have a typed variadic function in C++. So we cannot say that we want a function to accept arbitrary number of arguments of some specific type. Like this is not existent syntax or something like this. That should be a function template, in fact. But before C++20, to enforce that all the arguments are of the same type, we had to really use a bit more complex techniques. Yeah, so we could use, of course, enable if or just use some static asserts internally. But with C++20, it became much simpler because we can just use concept same as. Yeah, so we can say that every argument should have a type that is same as int. So this made it much simpler. So it's quite a small application for these concepts for the parameter packs. Okay, let's go further. Yeah, so we just restrict it to be int using concepts. And it's even shorter in the shorter form. So like really quite in the abbreviated form looks very nice, I think. Okay, now a bit about the bright future. So C++26 also will introduce some more facilities to handle the parameter packs. We will have direct indexing in the parameter pack. Yeah, so this is quite interesting feature. I would not say that it will have like will have, how to say this, like probably not for the daily usage, I think, but at the same time, there are applications where it can be necessary. So here, the template parameter pack can be can be inspected. Thank you. So we can take alias of the type, and also function parameter pack can be expanded. So we can take a value of argument. Those are all compile time constructs. But it is possible. Another feature that was added is also variadic structured binding. This is also looks very powerful thing, and this is an interesting example. Not examples. The feature will enable really some form of introspection. So the example demonstrates how. So we can have just a function template that would use the variadic structured binding. So here the pack items will represent the binded items. And so we bind items to the fields or items from any to the items of the value of some type that will be passed into the function, print field values. Yeah. So, and then we use the our folding expression to print the items. So we can actually print the values of those items. So in this example, we can just create some structure, pass it into this function, and get the items printed. So how this would work, it doesn't matter how many items and what are the fields or everything that can be structured, everything that can be used together with structured binding can then be binded to this pack, basically.
Well, you can print it, right?
Of course, I mean, this should, everything that is demonstrated here for all the types, it works if it compiles, of course. So, no, what I mean is that when we handle something generically, when we do the substitution, if substitution within the and the code that was generated as a result of substitution doesn't compile because some operations are applied to the type with which the template is instantiated are not supported, this is a substitution failure, basically. Yeah? So, and there's a much more about this, but generally, if there is no viable implementation, then that will be a compiler error. So that's same, and it was always like this, and it remains the same. Okay, so actually don't have any recap for this talk, because I think the talk was more like a recap itself. Yeah, not that much to summarize. I think that we can then switch to questions. Thank you very much.